Okay? In this picture, R1 is the refractivity of high refraction mirror. R2 is the refractivity of output coupler. If you are using metallic mirrors, R1 and R2 are just real numbers. Okay? But sometimes you can use, for example, total internal reflection or dielectric coating mirrors. Then R1 and R2 can be complex numbers. Have you studied this property before? 应该学过吧？如果你发生了全反射，那么这个反射率其实是一个负数哦。全反射只是它的绝对值是1，但是它会给你额外的 phase angle. Okay? So in that case, if R1 and R2 are complex numbers, certainly R1 times R2 is a complex number as well. Then what modifications do we have to make? Yes?
应该是只多一个相位的复数吧，因为你现在写成，你现在它是一个复数，你永远可以把它写成 exponential这一层的形态，所以它最后你的那个 total 的电场应该就只是要多一个 exponential 的复数。
Basically, you are right. But how do we modify these two conditions? Yes. For example, do we have to modify condition 1? Is there any difference? G equals LC. Is there any difference if R1 and R2 are complex numbers? No? So the condition is still the same, but you have to change maybe the formula of LC, right? Here, R1 times R2, but in the case of our interest, maybe R1, R2 absolute value. You got a new LC, but this formula is still correct. But how about the second one? So is the formula the same as before? Okay, so previously this one equals 2m pi. Now, what's the difference? You have some increment, right? Because the total phase shift is not just this one, but the total phase from R1 times R2. Okay? So in other words, your permitted frequencies is no longer m times delta f only, but some extra constant. Okay? 所以你的频率不再是 delta f 的整数倍而已了，它还有一个 shift 也就是这整个 spectrum 都有一个小小的平移 ，because of the complexity of R1 and R2. In that case, it's no longer commensurate. I will talk about this issue later. Okay? Perfect. Yes, so usually only high refraction mirror is total internal reflection is used there. Output coupler, you cannot use total internal reflection. In that case, no output you can have. So I want to show you some more details about commensurate. Okay? But let's take a time domain perspective. Commensurate means frequencies f has to be integral multiple of some mode spacing. So just like this figure, say we pick up one specific frequency f, which is integral multiple of delta f. Then in the time domain, this is time axis, you can see a single frequency in the frequency domain means a perfect sinusoid in the time domain, right? And if the frequency, say f equals f1 or fc1, is m times delta f, then in one round trip, your cavity round trip time, you have exactly the integral multiple of some carrier cycle. So starting with phase 0, end up with phase 0. Okay, perfect in phase. So if you have a time domain waveform coming from superposition of not only one but a lot of frequency components, but all of them satisfy with the commensurate condition, f equals m times delta f, what would happen? The synthesized electric field, E of t, no longer a simple sinusoid, right? Is strictly periodic. For every tr, you got exactly the same waveform. Okay? But if you have non-commensurate, your frequencies f satisfy with some common shift, usually referred by FCEO, plus integer m times mode spacing delta f, just like this picture. We pick up one specific frequency, satisfying with this formula. The sinusoid will not repeat itself after one round trip. Okay? Starting with phase 0, but ending up with no longer phase 0, right? So if you have a waveform synthesized by a lot of frequency components, okay, satisfying with this formula, then the field is not periodic, but the envelope is still periodic. So if you look down to the fringes, the synthesized waveform is not periodic. It cannot repeat itself after one TR. Okay. But if you only look at the envelope, it's still periodic. Okay. In the third case, if you have no cavity at all, you will have no so-called mode spacing. Then the synthesized waveform is no longer periodic, no periodicity at all. Okay, so this is a simple comparison between three cases: commensurate mode, non-commensurate modes, and no periodicity at all. Okay, so it describes the time domain behavior of commensurate or non-commensurate cavity modes. Now we can talk a little bit about dynamics, okay? But it's only qualitative descriptions, no formulas, just simple ideas. Let's take a look at this figure. What does the red curve mean? It means the field gain coefficient spectrum defined here. Okay? If you feel very weird, don't worry, it simply means the output spectrum function of omega means spectrum, a frequency domain function, right? Output spectrum divided by input spectrum should be equal to exponential to the g of omega, okay? So the g of omega is the gain coefficient spectrum, a function of frequency. It means for different frequencies, you have different gain, right? In this picture, maybe this central frequency has the largest gain, but for other frequencies, you have smaller gain, and the distribution following this curve, okay? And let's assume in the beginning, every frequency component has similar amplitude, similar energy. So the heights of different arrows almost the same. Okay? And the LC means the cavity loss. And this red curve is the peak of the red curve is higher than the LC. So it means you have to provide sufficient pump rate such that at least some of the gain spectrum is larger than the loss. Okay? That's the initial condition. Okay? If this happens, then you can imagine what's the next step of these frequency components. Okay? In the next step, you will see like this. Within this window, okay, these frequency components see larger gain than the loss. So after one round trip, they will be amplified, right? But outside this window, say here and here, things are reversed. Loss is larger than the gain. So these spectral wing components will be attenuated instead of amplified. So this is the output. The spectral wings become weaker. The spectral centers become stronger, right? But you see some new photons will be generated. So the red curve becomes lower, right? Because of the gain saturation I just introduced. Whenever you got new photons, you have to pay the cost. The cost is your gain is weaker. So this red curve becomes lower compared with before amplification, right? And this process will continue. I mean, central mode becomes stronger and stronger. Side modes becomes weaker and weaker. And the red curve becomes shorter and shorter, right? Until this happens. Even the central mode is only the same as the loss. So your central frequency reaches steady state. It will survive. All the other frequencies, the gain is always smaller than the loss, so they cannot survive. That's why in steady state, usually you will see a single frequency only. That's the working principle of CW lasers. Why do you have only one frequency? Because of this. Okay, so this is a simplified picture about CW laser dynamics. Initially, you have not only one frequencies, but a lot of them coming from the noise, maybe. But this process will guarantee in steady state, in principle, you can have only one frequency. And what is the frequency? Usually, it's the frequency of the largest gain, the peak of your gain spectrum. Usually, you have that frequency in steady state. Okay? Please.
Why is the gain spectrum in the bell shape?
It could be in other shapes. I just use a simplified picture. You know, for different gain media, you will see different shape of gain spectrum. Yes. So it's not always like this. But the idea is almost the same. Even you have different gain spectral shape, the dynamics still similar. Any other question? 好，所以没有任何公式。Yes.
所以它只要那个 gain 只有一个 peak 的话，它最后就只有一个那个 frequency 可以 survive，这样子。
简单说是，也有特例 ，like spectral hole burning effect, right? Spectral hole burning usually comes from, the gain medium can be categorized into homogeneous broadening and inhomogeneous broadening. This picture should be true for homogeneous broadening GAN media. Okay, but for in another case, inhomogeneous broadening effect, when some light get amplified, the GAN spectrum will not decrease altogether, but frequency by frequency. So you will see some dips in your GAN spectral shape. Then it would be different from this picture. And usually in that case, in steady state, you have multiple frequencies, not just single frequency. Okay, I admit it's true, but here we only talk about the simplest, the easiest example, homogeneous broadened CW lasers. Yes, please.
刚好有两个频段是对称于那个 gain 的 shape。
Yes.
那最后平衡的时候 gain 有可能会大于多少？
You mean your GAN spectrum has double peaks?
都一样，只是频率刚好是对称，左右对称。
左右对。
会刚好慢慢下来。然后刚好。不太好讲，就是刚好那两个频率它 gain 很 close 的时候，最上面那个却是高出来。
Oh, you mean in steady state, the peak of the red curve is above the loss.
因为旁边有两个刚好对称的把它
顶住，中间没有，你的意思中间没有 mode. It's possible in theory, but think about the mode spacing in practice, right? The typical size of lasers, the cavity size in the order of 1 meter. So the mode spacing is tens of megahertz. And the GAN spectrum, of course, there are many different GAN spectrum, but usually tens of megahertz is a very small number compared with the GAN spectral width. 所以我的意思是，通常我这是简化的画法，一个 GAN 的 spectrum 的宽度叫做 GAN bandwidth， 通常会远比这个 mode spacing 正常的雷射的 mode spacing 大很多。也就是在这个下面可能有非常稠密的 modes。So that case is very rare， 因为间距太小，很难做到像你刚刚讲的那个情形。Unless you purposely make a very short laser cavity using microfabrication， 你做半导体制成，把 cavity 做得极小 ，then mode spacing could be very large. In that case, it's possible. Okay, so it's a matter of practice, reality, but in theory you are right. Then we need to do some mathematics. Okay. For simplicity, I only talk about 4-level systems. This is the energy diagram of 4-level system. Level 1, the ground state. Level 2, level 3, level 4. Okay. So W is referred to pump rate here. Okay. The physical unit is 1/second. Okay. So it means how many percentage of ground state electrons pumped to excited states, level 2, in 1 second. 好，所以我用中文讲一次哈。这个 W 的意思是什么？1秒钟之内有多少的 electrons 可以从 level 1被送到 level 2 That's the meaning of pump rate. Of course, the stronger pump you provide, you have a larger W. Okay? And this pump rate interacts with levels 1 and 2 only. Nothing about levels 3 and 4. Okay? Relaxation times. We have actually 3 relaxation times, but let's take a look at tau 2-3 and tau 4-1 first. Tau 2-3 and tau 4-1 are very short. say less than 1 picosecond. So roughly it means within tau 2 she, a time interval of tau 2 she, electrons on level 2 will be dumped to level 3. 就是大概在这个时间之内，所有在第2阶的电子就会掉到第3阶。所以这个时间越短，就代表什么？它很容易 dump， 很快的就 dump 下去。OK， 那它们都非常短。所以 you can imagine electrons can rarely stay on level 2 and level 4. Okay? And it's of great advantage because if tau 2 she and tau 4 1 are very, very short, then it's very efficient to create population inversion. Why? As I mentioned, if they are very short, that means electrons on level 2 will be quickly dumped to level 3, then staying here. And this is the upper state for laser transition, right? Laser transition happens for between levels 3 and 4. If you want to have population inversion, you need a lot of electrons on level 3 and almost no electrons on level 4, right? Then you have large population inversion. It relies on short relaxation times on these 2 levels. Okay. So the logic is, if these 2 conditions are not true, this material is not good to be a laser gate medium. Only those with short relaxation times here can be used as laser gate medium. 逻辑是这样。我常常被问到为什么那么刚好，它一定会很小？不是这样，很多材料这个不小，但是如果那样，这个材料就不会被拿来做 gate medium。凡是被拿来做的，基本上这2个都会很小。Okay, and it's assumed in our model.